Okay, we're going to talk about, excuse me, a topic called inner product spaces. And let's go right into the definition. An inner product on a real vector space V is a function. Okay, a function has an input that's going to assign it to exactly one output. And the input is going to be two vectors. So it outputs a real number or associates a real number. And this is the way we denote that real number. I'll talk about that in a minute. Where u and v, those are vectors in the vector space capital V. And this real number, or this operation that assigns two vectors in the vector space to a real number, has to satisfy these four axioms. Okay, the first axiom is, and when we say this thing is the inner product of u and v, inner product of u and v. Before I go through this, let me just explain again this notation. First of all, when we talked about vectors before, some of you remember in Calc 3 you might have used these less than and greater than symbols to denote around the components of a vector. Well, here in linear algebra, that's why we don't use these symbols for those n tuples. We use them for the inner product. And notice in here we have vectors. See the arrows over them. In the textbook they would be bold-faced. So this really is something, you know, when we're doing an operation given two inputs, we typically put a symbol in between them. Think the addition symbol, right? We put a plus sign between two numbers indicating we add them to get a real output, right? Or we have the minus sign, or multiplication or division sign. Or that's for real numbers. What about vectors? What sign have we used for vectors? Well, we've used a dot which represented the dot product, right, between. And there's other symbols that you can use to denote the operation you want to define. So this is a different way of doing that. Instead of doing u plus v, or u minus v, or u divided by v, or u dot v, we use this notation. Okay, so this takes two vectors, a pair of vectors, and outputs a real number. So when you see this inner product of u and v, this symbol, this is a real number. This is a real number, a scalar for us, right? And so the first axiom that has to be true for the inner product is essentially like a commutative property. The order doesn't matter. They talk about this as being the symmetry axiom. Another one is, they call it the additivity axiom. It's more like a distributive property in a sense. If I take the inner product of the u plus v, right, which is the standard addition in the vector space for vectors in the vector space. If we take the inner product of u plus v with w, that's, so the comma separates the two vectors that we are doing the inner product of, right? We're taking these two vectors. It's going to be equal to the inner product of u and w plus the inner product of v and w. So sort of a distributive property in a way. Then the next one says if I take a scalar multiple of a vector, which again the scalar multiplication defined for that vector space, times ku times the inner product of ku and v, we can bring that scalar out. So it's the scalar times the inner product of u and v. Remember, the inner product again is a real number. So on both sides of these equal signs all the way up, we have real numbers. And the last one says if I take the inner product of the vector with itself, it's always going to be non-negative, greater than or equal to 0, with equality, right? The inner product of the vector v with itself is going to be equal to 0 if and only if the vector is the 0 vector. Okay, now the thing I want you to think about for an inner product then is indeed the dot product. Okay, that is a specific example that we are familiar with of an inner product, but there are many, many more. In fact, there are many more for different vector spaces. And when we say many more, well, they have to satisfy these four axioms, of course. So if we have an inner product, it's going to satisfy these four axioms. Now, if we go back to the dot product, u dot v is equal to v dot u, right? And u plus v, that expression dot w is u dot w, v dot w, and so on. These four axioms, if you go back to when we talked about the dot product, or what we call the, by the way, Euclidean inner product, and now you know why we call it the Euclidean inner product, it satisfies these four axioms. In fact, I mentioned that fact in that lecture, that we would be coming back to the four axioms we said were true for an inner product and using it again later, and here it is. Now, a real vector space that has a defined inner product is called the real inner product space. Now, one thing we're going to see real important is the inner product is going to help us extend the concept of measure to a vector space. Okay, it's going to help us define distance between vectors in the vector space. Okay, it's going to help us define the length, or what we're going to call the norm of vectors. And remember, vectors are not just ordered n tuples, but they're also matrices, right? 2 by 2 matrices, 3 by 3 matrices, 4 by 3 matrices, or polynomial functions. Remember, x squared plus 2x plus 1, for instance, right? They are vectors in different vector spaces, and so we're going to have a way to measure those vectors. What is their length? What's the length of a matrix? What do you mean? We are going to be able to define that. What's the distance between two polynomials? What do you mean? We're going to be able to define that with a given inner product. Now, the Euclidean inner product on n space is something we're familiar with again, and it's defined as follows for two vectors in n space, right? Here they are n tuples. Then the inner product of u and v is our simple Euclidean inner product that we've called the dot product before, but now we'll call it the Euclidean inner product. That's exactly what it is. So that's the one we're familiar with. So always think about that. But again, this is not the only one. Once you have a defined Euclidean inner product, be it the Euclidean inner product or any other, then we can define these concepts here. So if V is a vector space, a real inner product space, then the norm or length of the vector V is denoted this way, and the norm is equal to the square root of the inner product of the vector V with itself. And this should come back to when we were talking about the dot product, right? Because when we had the dot product or Euclidean inner product, we said the norm of the vector V in n space in Euclidean inner product space now was the dot product of V with itself, and then we took the square root, right? That's how we calculated the norm before, or that was a relationship that we used before. So it makes sense here. So notice the norm or length of a vector depends on what the inner product that is defined for the vector space. If you change the inner product, the norm is going to change. The distance between vectors u and v, denoted this way, is the norm of u minus v. Or, by the way, the norm of v minus u. It doesn't matter the way you subtract here, but norm of u minus v, which, just going back up to this definition, is going to be the square root of the inner product of u minus v with itself. Okay, so it takes a little bit to get used to this notation. It's a little different than maybe what we've dealt with. But again, think of your common one, the Euclidean inner product, and then, of course, we're going to be using other inner products, but we will use those. Now, a vector then has a norm of 1, or if a vector has a norm of 1, it's called a unit vector. Okay, so we're going to be able to define unit vectors not just in n space, but in M22, the set of 2 by 2 matrices. What's a matrix that is a unit vector? What do we mean by that? We'll be able to define that. What's a polynomial? Vectors in P sub 2, the set of all degree 2 or less polynomials. Those are vectors, right, in that sense. What is a unit vector in such a space? We'll be able to define that. And then more importantly, right, once we have this idea down, then, well, we have some other properties, and these are fairly easy to prove. If we have two vectors in a real inner product space and k is any scalar, then the norm of any vector must be greater than or equal to 0. It's pretty clear the way this is defined, and going back to the definition, right, of the inner product of a vector with itself being non-negative, we know that this quantity has to be non-negative as well, with equality when the vector's norm is equal to 0 if and only if the vector is the 0 vector. Remember, the norm And of course, the inner product is a scalar. The norm of any scalar multiple of a vector v is the absolute value of that scalar times the norm of v, because remember, it has to be the absolute value. If k is a negative number, we can't get a negative output because, again, the norm is always non-negative. As I said, the distance from u to v is the same as the distance between v and u, and the distance between any two vectors is non-negative, and again, equality if and only if we are talking about u and v being the same vector. Okay, so these are pretty obvious properties. This is section 6.1 in the book that I've just went through in a nutshell. and you want to see what section 6.2 is, orthogonality. Well, two vectors u and v in an inner product space are orthogonal if their inner product is what? 0. And that's an extension for what we talked about with the dot product, right? In n space, in Euclidean space, the inner product, the inner product or the dot product of two vectors being equal to 0 indicates they were orthogonal. And we're used to that in 2 and 3 space, but we extended that right to n space. Now we'll be able to talk about orthogonality in other vector spaces. What does it mean for two matrices to be orthogonal to one another, say in M22? What does it mean for two polynomials to be orthogonal to one another in P sub 2? Okay. Now, this seems rather abstract, maybe, but there are lots of applications where we would want to be able to define inner products different way, again, because they give us a sense of measure, distance between things in the vector space. And there's lots of areas where things like this can become quite useful. My main goal in this for you is to understand and to apply these different inner products, and we'll give you an example in this basically is it for chapter 6, but let's look at some examples, of course. Okay, so let's start in our familiar vector space. Let's start in 2 space. For two vectors in 2 space, we're going to define the inner product of u and v to be this: 9u1v1 plus 4u2v2. Again, u1, u2 are the components of the vector u, v1, v2 are the components of vector v. You say that looks something like the Euclidean inner product or dot product, except we've got this 9 and 4 here. Well, is this, first of all, an inner product? So remember, we have these 4 axioms to show, and that's what I'm going to do. I'm going to first show axiom number 1 holds. And so I'm going to start with this side, inner product of u with v, and I want to get to the other side. Well, what is the inner product of u with v? Here's the definition. Again, I'm thinking u is this vector and v is this vector. It's going to be 9u1v1 plus 4u2v2. However, these are all real numbers, right? u1, v1, u2, v2, all real numbers. I know that multiplication of real numbers is indeed commutative, so this is the same as 9v1u1, just commute the order there, plus 4v2u2. But then by definition, right, if this is uv, then this would be, again, vu. And we have the symmetry axiom satisfied. Okay. The next is the additivity axiom, so let's look at that. That starts with the vector u plus v. And what would that be? Well, again, the definition is 9 times u1 is the first component of this first vector. This first vector is u plus v. What's the first component of the vector u plus v? Well, the first component of the vector u plus v will just be by standard vector addition, right? u1 plus v1. And then times v1, which is the second component, right? In this case, or the second vector's first component, rather. And w is that. So we're going to use the convention, same thing, right? W would be w1 comma w2. We'll do that, right? So there's w1, right? Again, all real numbers here. Plus 4, the second component of this first vector is u2 plus v2. And the second component of w is w2. Okay, now what am I trying to get to? I'm trying to get to this, and I can get there. First of all, notice I have a distributive property. I'm going to distribute the 9 through, and I'm going to distribute the w through. So this will be 9u1w1 plus 9v1w1. Distributing the 4 through here, 4u2 and the w2 plus 4v2w2. So just distributive property, these are all real numbers. Then I'm going to regroup, right? I'm going to regroup. This will be 9u1w1, and I'm going to pull in the 4 plus 4u2w2. I'm going to kind of group those guys together. And then I'm going to group the other two, v1w1 plus 4v2w2. All right. And what is this? What is 9u1w1 plus 4u2w2? Well, if you come up here, that's going to be what? The inner product of u with what? W. All right. This is equal to the inner product of u with w, which is written that way. And this is going to be what? The inner product of v with w. And that shows, right, the additivity axiom that we were trying to show. Okay, u plus v, the inner product of u plus v with w is the inner product of u plus w plus the inner product of v plus w. So 2 down, 2 to go. The homogeneity axiom, right? Let's take a look at that. Start with the inner product of a scalar multiple of the vector u. And I'm trying to get that to be k times that inner product. Well, again, by this definition, what do we have? 9 times the first component of our first vector. What's the first component of our first vector there? Ku. Well, that'll just be k times u is just ku1, ku2, right? So that first component will be ku1, and the first component of v, of course, is v1, plus 4. Second component of ku is ku2. Second component of v is v2. And then notice that both of these have that common factor of k now. These are all real numbers. K is a scalar, is a real number. I can factor out that k. And what am I left with? 9u1v1 plus 4u2v2. And what is that? That is, by definition, the inner product of u with v. And I have shown the homogeneity axiom, number 3, is satisfied. Last one is the positivity axiom. I'll take the inner product of the vector v with itself. Of course, then I've got what? 9 times the first component of this vector v is v1, and the first component of this vector is v1. So I've got v1 times v1, or v1 squared. And then 4 v2 v2, or v2 squared. Okay. Well, clearly this expression is clearly going to be greater than or equal to 0 because I'm squaring v1 and v2. So even if v1 or v2 is a negative number, if I square it, I'll get a positive result. So this will always be a non-negative result with, right, equality, meaning being equal to 0, if and only if what? The only way for this expression to be equal to 0 if both v1 and v2 are both 0, which would mean the vector v would have to be the 0 vector. And so there we have it. We have proved that this defines an inner product on 2 space. Okay. Now, what can we do with an inner product in 2 space? Well, we can define norm or length, right? Norm and distance between vectors. So let's do it. Let's find the compute, first of all, this inner product, right, using this inner product. So real important, using this inner product. What's going to happen is a lot of you will revert back for some reason to the Euclidean inner product, the dot product, because you're just used to it, I understand. But you must use the inner product that I give you. If I give you an inner product like this, and I say use this inner product and answer these questions in this inner product space, right? You have to use that inner product. If you don't, I don't know what to do. This is essentially, I mean, for engineering students, this is great, right? This is plug and chug. It's just, let's just plug in and evaluate. So the definition is 9u1v1 plus 4u2v2. So it's going to be 9 u1 in this case, the first component is -1 for the first vector times the first component in the second vector 2. So there's u1 v1. So this is like the u and this is like the v. Plus 4 times u2 v2. That's 2 times 3. All right. So I'm embarrassed, right? This is it. Just compute that number, right? You get what? -18. Wait, there's, oops. That shouldn't be a 2. I'm sorry. I don't know what I did there. 5 is the second component of u. I'm sorry for the confusion. I don't know what there's no telling what I said a little while ago, so just neglect that. 4 times u2, which is 5, v2, which is 3. 4 times 5 is 20 times 3 is indeed 60. Okay, let me slow down a little bit. I go too fast. I'd say it's easy, but then I make a simple mistake. Okay, so 42. So again, you get a real number. Remember, inner products take two vectors and output a scalar. Okay, that's it. Let's take a look at this. Are these two vectors, and these are the two vectors we just found the inner product of, are they orthogonal in this inner product space? Okay, how do we determine orthogonality? Well, remember we talked about that right here. They're orthogonal if what? Their inner product is 0. If their inner product is 0. And so I go and I look, the inner product is 42. It's a real tough thing. So what's the answer? No. And why? Since the inner product of these two vectors is not 0. That's the bottom line, right? So if it is 0, then they're going to be orthogonal to one another. Okay, in this inner product space. So be careful when you hear the word orthogonal. You're thinking 90 degrees. You're thinking dot product. Not necessarily. Only if you're using the dot product. We're not using the dot product, so that's different. Things are different now because we have a different measure on the vector space. In fact, talking about measure, what is the magnitude or norm of the vector 2 comma -2? And this is where a lot of people mess up and they go back to the Euclidean inner product. This is in this inner product space. I have to use this inner product. And remember how we defined norm right here, right? So it's going to be the square root of the inner product of the vector with itself. So by definition, this is the square root of the inner product of the vector, which is 2, -2, with itself. Now, one thing, it's tricky how to write this out correctly. So notice the inner product has a comma separating the vectors always. Okay, you'll have the less than sign, greater than sign on the right. You'll have a comma in between, and you'll have two vectors. Now the vectors, I'm covering them up with my fingers, but they could be anything. They can be ordered pairs like they are here. They could be ordered n-tuples. They could be polynomials. They could be functions. They could be matrices. Okay, here they're ordered pairs. Notice the ordered pairs, of course, have a comma separating the two numbers inside parentheses. So there's a lot of commas going on. Be real careful that you understand the notation and you write it out correctly. Okay, now how do we determine this inner product? Don't use the dot product. Use this, right? This is what's given for this, right? So this would be the square root of 9 u1 v1, 2 times 2. Well, that's just 2 squared. Plus 4, remember, right? Plus 4 u2 v2. -2 times -2 is -2 quantity squared, so be careful what we get. Now we just compute this number, right? I get 9 times 2 squared is 4, 9 times 4 is 36, plus what? 4 times -2 squared is +4. 4 times 4 is 16, right? We're not going to get any negative results when we square a negative number. 36 plus 16 is the square root of 52. There's the answer. If you want to really impress me, then you might recognize the fact that 4 is a factor of 52, and so I can write this as the square root of 4 times the square root of 13. 4 times 13 is 52, which is 2 square root of 13. So I would be really impressed with that, but I'm fine with that. Okay, so no, not really impressed, but okay. Again, it's just going to be the length or norm for this vector. Now, if you use the normal inner product, sorry, not normal, but the Euclidean inner product, the dot product, you're going to get a different result. And in that case, I don't know what to do other than it's wrong. You didn't follow directions. So please follow directions on this test. It's easy. You just have to follow directions. Use the inner product given. Same thing here. What's the distance between two vectors? It's defined by the inner product, right? It's the norm of u minus v. And again, using this inner product. Whatever inner product is given, you will be given an inner product. Use it. Okay, so this is the norm of u, which is 1, negative 2, minus v. Okay, now you've got to do the operation here, which is really subtraction would really be what? Adding the negative 1 times this vector. But we can go ahead and just subtract components, right? So this will be 1 minus 0. And negative 2 minus a negative 4, negative 2 minus a negative 4, negative 2 plus 4 is 2. Sorry. So I'm now I'm going back to the problem I just did. Instead of finding the norm of 2, negative 2, I'm finding the norm of 1, comma 2. So it's the same thing. It's the square root of the inner product of this vector with itself. Which again, using this inner product, 9u1v1 plus 4u2v2 is 9, right? 1 times 1, or 1 squared, plus 4, 2 times 2, 2 squared. And now we just compute this. This will be 9. 4 times 4 is 16. I get the square root of 25, which is 5. A nice whole number there. Okay, that's the distance defined under this vector space. Okay, so we're going to stop here. In the next video, what I want to take a look at is what is the effect of this inner product on 2 space in terms of measurement? How does it compare with the dot product, the Euclidean inner product that we're used to? What's the difference? And so we're going to look at that a little bit. We're going to talk about unit vectors a little bit in these 2 vector spaces and sort of compare it from that standpoint. And then we're going to look at some inner products defined on other vector spaces other than n spaces like 2 space and 3 space. Like we're going to look at inner product on a matrix space, a set of all 2 by 2 matrices, and we're going to look at a measure on another vector space that we haven't talked about a whole bunch, but it's a function vector space, and it will bring in a little calculus. So looking forward to that. That'll be in the next video.